Alright, this is the second video of 10th week, and in this video I'm going to talk about exponential and logarithmic functions. So I'm going to talk about chapter 10 in the textbook, where we are going to study two important types of transcendental functions, exponential and logarithmic function. So I first divide the chapter into three subsections, and in the first subsection we are going to talk about basic properties of these two functions. In the second, we are going to study how to take the derivative. In the third, we are going to study some applications. Alright, so the main topics in chapter 10 are two transcendental functions, exponential, that looks like this, and logarithmic function. Okay? So let me first talk about exponential function. So if you compare this exponential with what we have seen before, that is a polynomial, okay? X squared, for example, then you can easily see that these two functions have the same basic components. Okay? Polynomial has the base and the exponent, and so does exponential function. And then the only difference is we interchange the exponent and the base. So in polynomial, variable is the base is the variable. Okay, so we fix the exponent by some constant. So exponent is given by constant, and we change the size of the base. But in exponential function, in contrast, now the exponent is variable, and the base is given by some constant. Okay? So, although there is a subtle difference between these two, the way to treat the exponential function is quite different. So we are going to study that. And the second transcendental function is logarithmic function. So I'm not sure if you have seen this type of function, but logarithm is defined as the inverse of the exponential function. So it turns out that there are very close relationship between these two functions. So the most properties of logarithm are inherited from exponential functions. So you may wonder why we have to study this, why we have to learn about them. So to provide you motivation, let me start with some concrete example. Short answer for why we have to learn about this, because they turn up in every discipline, and economics is not an exception. So if you continue to study economics or finance, you're going to see them several times. Okay? So let me show you one concrete example. Suppose that you deposit $1,000 into a saving account, and then the account promises to pay you 5% of interest per year. Okay, so let me draw the timeline to illustrate this situation. So you deposit $1,000, okay, and then interest rate is given by 5%. That means at the end of each year, you can earn $50. So the bank pays you $50 for the interest on your deposit. So after 1 year, the value of your account, $10.50. In 2 years, $1,100. In 3 years, $1,150, and so on. So that increases proportionally or linearly. But this describes the case of simple interest. Okay. And if the interest is compounded annually, then the first year is the same. At the end of the first year, you're going to get 50. But at the end of the second year, okay, you're going to get 50 for the interest on your initial investment. That is often called the principal. Okay, so that is the same. But additionally, the interest of the interest. So the interest of this 50 you earn at the end of the first year is also added to your bank account. Okay? So literally, interest is compounded. Okay? So in this case, if you think about the bank balance at the end of the second year, you have 1,050 and another 50, and plus 5% of this 50, that is $2.50. So total you have 1,000 times 1.05 squared. Okay? And 3 years from now, 1,000 times 1.05 cubed, and n years from now, 1,000 times 1.05 to the power n. Okay? So it grows exponentially. The value of your account grows exponentially. Okay? And then you can see that this is an exponential function. So regarding this, the value of your account as a function of n. So for each number n, this function gives us the value of the account. So the future value of the account, okay, and the future value follows some exponential function. All right. So when we compute the future value, exponential function appears. Okay. And then logarithmic function. Suppose that you wonder how long you have to wait for your account to become double. So how many years you have to wait for your account to be 2,000? Right? To figure it out, we have to set the equation. So we have to set this value to be equal to 2,000, and we needed to solve this equation for n. Okay, and logarithm help us to find the solution. So help us to solve this equation for n. Alright, so the logarithm is defined as the inverse of this exponential function. So it turns out that these two functions have a very close relationship. Okay. Alright, so in general, the future value of an asset increases exponentially with time. So if you think about future value of k dollars t years from now, okay, now we regard this as a function of time t. Okay, then k is the present value of the asset, so indicates what you have right now in your hand. It's the present value. Okay, and the r indicates the annual interest rate, and n is the number of compounding per year. So if the interest is compounded annually, n is going to be 1, quarterly, n is going to be 4, daily, 365. Okay, and t is the number of years. Okay, so the future value t years from now, so future value of k t years from now is going to be so when interest is compounded n times per year, k times 1 plus annual interest rate divided by n, and raise this number, so raise the number in the parentheses to the power of nt. Okay, so for example, if the interest is compounded monthly and the rate is given by 5%, future value of 1,000 1 year from now is going to be, now we enter the value we know, so 1,000 for k, and 0.05 in decimal forms for r, and 12 for n, and t for 1. So 1 for t. Okay? Then we're going to have a 10,051, so slightly more than what you have if the interest is compounded annually. Okay. So once again, this is an exponential function. One example of exponential function. Now we regard this function as a function of time t. So it tells us future value of some asset whose value is given by k t years from now. Okay? And once again, k is the present value. So we can see the relationship between future and present values from this equation, from this formula. So future value is going to be present value times 1 plus r over n to the power nt. Okay? And if we this equation, so if we solve this equation for PV, present value, then we are going to get present value is equal to future value times reciprocal of this operator. So present value is going to be future value times minus, so now the power becomes negative, negative nt. Remember, x to the power 1. So negative exponent means the reciprocal. Okay. So if we divide both sides of this equation by this operator, then we are going to have negative exponent. Okay. So suppose that you earn, say, $5 million in 10 years. Then what is the present value of that earning, future earning? And if you know interest rate, and if you know how many times interest is compounded per year, then you can use this formula to find the present value. Okay. And this is some theoretical question. So suppose that if the interest is compounded continuously. So interest is compounded every second, and then that earned interest is added to the bank account every second. Then, going back to this formula, and then we want to check, we want to compute the future value of 1,000 1 year from now. Okay? If the interest is compounded continuously, that means now n is going to be infinite. So infinite number. So we have to take the limit to evaluate this future value as n goes to infinity. Okay? So of course this is impossible in practice, but in finance theory, it gives us a nice approximation of future value if the interest is compounded many, many times. All right? So it can be used as a proxy for the when interest is compounded many times. So in this case, if you take a look at this expression, so when we evaluate this limit as n goes to infinity, you may attempt to say, because the exponent goes to infinity, so, and we have some number larger than 1 in the parentheses, it goes to infinity. Okay? But it turns out that it converges to some finite number, well-defined finite number. Okay? And furthermore, one advantage of this continuous compounding is the formula is remarkably simple. Okay? So it can be widely used for, computation of future value. So the approximate future value of financial asset. All right, so I think this is enough for a motivation. So exponential function or logarithmic functions appear in some economic context naturally. Okay, and now let me talk about exponential functions. So simple exponential function takes a form of this. So b to the power x, once again, base is given by constant, and now we change the size of exponent. Okay, so exponent is given by variable x. All right? And then we're going to put some restrictions on the base. So base is going to be positive number other than 1. Okay? And the reason is we want to avoid some unpleasant cases. So if b is equal to 0 or 1, and this exponential function boils down to constant. Because when base is equal to 0, 0 to the x, that is always equal to 0 for every positive value of x. When x is negative, the function is undefined, right? Because 0 to the negative 1, for example, that is 1 over 0, right? Because negative exponent means reciprocal. So 1 over 0 is undefined. So for negative value of x, if the base is equal to 0, the function is undefined. If the base is equal to 1, then no matter what x, we are going to get constant 1. Okay? So we use exponential function to model exponential growth, but when base is equal to 0 or 1, it gives us constant, so that is not interesting case. So we rule out these two constants. So we rule out these two bases. And we also rule out negative bases because when base is negative, we have real numbers for some values of x or complex numbers for other values of x. So for example, if base is given by negative 4, negative 4 squared, so when x is equal to 2, that is a well-defined 16. So if we multiply negative 4 2 times, we are going to have 16. That is a real number. But negative 4 to the power 1/2, that is equivalent to taking square root. But square root of a negative number is undefined. Then we have some complex number 4 times I, imaginary number, but we are not going to study this imaginary number in this class. So we exclude negative base as well. So we are going to consider only we are going to consider only exponential function with positive base other than 1. Okay. In the end, we are going to focus on some specific type of exponential function. So when base is equal to some special number, okay, and that is larger than 1. So here is the graph of exponential function when base is equal to 2. Okay, so that grows exponentially, as you expect. So when x is equal to 1, it gives us 2. At 2, 4, 3, and 8. And when x is a negative value, say negative 1, 2 to the power negative 1 is 1/2. 2 to the power negative 2, 1/4. Negative 3, 1/8. So you can easily check that when x grows large to negative infinity. So when x is very close to very large negative number, the function is very close to the horizontal axis. So the value of the function will be very close to 0. Okay. So here I enumerate the basic properties of exponential function. So let me first talk about the first two general properties. So these two properties are valid no matter what base b is. So regardless of this base b, okay, function's value at 0 is equal to 1. So f of 0 is equal to 1. So b to the power 0 is always equal to 1, no matter what base b is. Okay? Because we already put some restrictions on the base. So we focus on the case when base b is a positive number other than 1. Okay? So in this case, so with this restriction on base b, b to the power 0 is always equal to 1. Alright? So that means the graph of this function, exponential function, always passes through point 0, 1. So the graph of fx will be through 0, 1. Okay, like this one. Okay. Here, if you take a look at the orange line, so there is a one exponential functions graph. It passes through the point 0, 1. Okay. And the second general property is, no matter what base b is, the function gives us positive value. Okay, for every value of x. So the function will never be 0. So the image of this function is from 0 to infinity. Okay? So the graph of the function appears in the first and the second quadrants. Alright? So it takes a positive value. And the third property, so the third property indicates when base is larger than 1, so if b is larger than 1, then function is monotone increasing. Okay, function is monotone increasing. So you can take an example, say 2 to the power x. Okay, when x grows, you can easily check that this function also increasing. Right? So when x approaches infinity, so when x grows large, the function also grows large. So it grows to positive infinity. On the other hand, when so when we take the limit as x goes to negative infinity, the function will be very close to 0. So think about it, 2 to the power negative 1 million. Okay, this is the same as 1/2 to the power 1 million. Right? Once again, negative exponent is a reciprocal. So we first take the reciprocal and then raise to the power 1 million. Okay? And if you multiply 1/2 1 million times, you're going to get very, very small number, very tiny number. Okay? So when x grows to some large negative number, okay, then the function will be very close to horizontal axis. But it never touches the horizontal axis. Okay? Because of the second property. F of x is always larger than 0. And the last property, and now when base is some number between 0 and 1, say 1/2, okay, then function is monotone decreasing. So when x grows, the function converges to 0, but when x grows to negative infinity, then the function goes to infinity. Okay, so this is easy to understand once you catch the relationship between these two. 2 to the power x and 1/2 to the power x. Okay, so let me call this function f of x. Then this is going to be f of negative x. Because, if we substitute negative sign for x, then this is going to be 2 to the power negative x. That is the same as 1/2 to the power x. All right? And then relationship between f of x and f of minus x. The graph of f of minus x, so f of negative x, is going to be reflection of this f of x above the vertical axis. So these two functions graphs are symmetric with respect to the vertical axis. So if we have, 2 to the power x looks like this, right? Then 1/2 to the power x, so when base is at some number between 0 and 1, we are going to have this graph. Okay? That is exactly symmetric with respect to the y-axis. Okay? So when x grows to infinity, the function converges to 0. But when x approaches negative infinity, so in the opposite case, function grows to positive infinity. All right. So this is a simple exponential function. When base is given by some constant and exponent is given by some variable. Okay. But as I told you before, we are going to pay attention to special type of exponential function, that is e to the power x. So when base b is equal to some number e. Okay. So this number e, so now let me define this number e. So this is a number. This is not a variable. This is some irrational number, just like the number pi or square root of 2. Okay? So this number e is not a variable, it's some constant. And there are several ways to define this number e, but in the textbook, the definition is given like this. So we consider function f of x given by 1 plus 1 over x raised to the power x. Okay? So first of all, this is not an exponential function because we have a sum, so the base is not a constant. We have another variable x in the parentheses. That means base is not a constant. It also changes over x. And this is not a polynomial either because the exponent is given by x. Okay, so this is some, nonlinear function, general nonlinear function. Okay, now we increase the size of x from 0 to infinity. Okay, so let me start with the number 1. When x is number 1, then f of x becomes 2 to the power 1, so that is 2. So when x is equal to 1, the function is going to be 2. When x equals 2, 1 plus 0.5, so 1.5 is squared, that is 2.25. 2.25. Okay, so it grows from 2 to 2.25, so it increases by 1/4. When x equals 5, now 1.2 to the power 5, that is 2.488. When x equals 100, 1.01 to the power 100, that's 2.7 approximately. Okay, so when x increases, you can easily check that the number in the parentheses decreases, right? Because when x is on the denominator. On the other hand, the size of exponent increases. Okay, so it is not that. So when x grows large, the number inside the parentheses converges to 1. But the exponent also grows to infinity. So it's going to be 1 to the power infinity, or some 1.00001 to the power infinity. In this case, the function grows to infinity, right? Even though this is very slightly larger than 1, if we multiply the number infinite times, we are going to get very large number. So it may approach infinity, or if we first take the limit inside. So if we take the limit, the quantity inside first, that is going to be 1 when x grows to infinity. And then we take the limit, we take the power of x. Then 1 to the power infinity, that is still 1. Right? So it's a very, this is very, non-trivial to set the value of this. So asymptotic behavior of this function. When x grows large, what is the value of this function? All right? And then it turns out that it does not grow to infinity. This function does not grow to infinity, and it's not either, so it's not equal to 1 either. Okay? In fact, it turns out that f of infinity, so when x grows to infinity, so the limit value of this function as x goes to infinity is equal to 2.718 something. So this is an irrational number. So there's no repeating decimals, and it goes on forever, just like number pi and square root of 2. So this function, f of x, grows to this specific number as x grows large. So this was discovered by one of the greatest mathematicians, Leonhard Euler. So this number is named after him, often called Euler's number. Euler's number E. Okay, so once again, E is not a variable, it's some constant, irrational number. Okay, and then we are going to focus on exponential function with base number E. So e to the power x. Okay, so e to the power x, this function can be written as exponential of x. So in short, exp of x. So whenever we have some lengthy exponent, say e to the power 1/2 x squared plus 1 over x minus 5. So if we have a lengthy exponent, it can be written as exp of the exponent, like this. Okay, it's the same expression. Okay, once again, this is the exponential function with base number e. Okay, And this is called a natural exponential function. Okay? So because E is some number between 2 and 3, so 2.78, so the graph of this function lies between 2 to the power x, so this is a 2 to the power x, and 3 to the power x. Okay? So here the green colored curve displays the graph of this natural exponential function. Okay? So natural exponential functions graph lies between 2 to the power x and 3 to the power x. Alright? And we are going to focus on this natural exponential function because this function has a very beautiful features and unique features. And furthermore, every exponential function, b to the power x, can be represented by this exponential function. So we can convert this b to the power x to the e to the power x. Okay? So every property of this b to the power x is from the exponential function. So it's enough to study the natural exponential function. Now we are going to focus on this e to the power x. Right? And finally, this number e can be used to compute the future and present value of an asset when interest is compounded continuously. So going back to motivating example, so if the interest is compounded continuously, what is the future value of 1,000 1 year from now? Okay, then this is going to be in light of this formula. Okay, we put in 1,000 for k, 0.05 for r, and 1 for t. Okay. Now the problem is, because interest is compounded continuously, that means n goes to infinity. Okay? So now we take the limit of this operator as n goes to infinity. Okay? But this is going to be, so how to evaluate this limit? Because we know 1 plus limit of 1 plus 1 over n to the power n as n goes to infinity is some number e. Okay, so here we have, instead of 1, 0.05. So how to evaluate this limit? As n goes to infinity, 0.05. So let me first modify this function to 1 plus 0.05 divided by n. And then for the exponent, let me first divide by 0.05 and then multiply by 0.05. Okay? So I divided by the same number and multiply by the same number, so these two are cancelled. So this limit value, the value of this limit is the same as this one. Okay? Then with this, modify the limit, what can I do? Because when n goes to infinity, n over 0.05 also goes to infinity. So let me call this n prime. So n prime is n over 0.05. When n goes to infinity, it is self-evident that n prime also goes to infinity. Okay? So I let n go to infinity is equivalent to I let n prime go to infinity. So with that in mind, I can rewrite this limit as limit n prime go to infinity, okay, 1 plus 1 over n prime to the power n prime, and then raise everything to the power 0.05. Okay, then you can easily see that the limit inside the parentheses converges to number e. So this is going to be e to the power 0.05. Alright, so with this method, of evaluating this kind of limit, now let's think about the future value formula. Okay, so future value of k t years from now, when interest is compounded continuously, the general formula is going to be this. Okay, we take the limit as n goes to infinity. Then you can easily check that with the same method, this converges to k e to the power rt. Okay, so we have a really simple formula for the future value. Okay, so it can be expressed as an exponential function, natural exponential function. Okay, and the present value of k, so this k occurs, so this revenue k is realized in t years. Okay, then what is the present value of this k? That is a k times the reciprocal of this, so k e to the power negative rt. Alright, so with this natural exponential function, we can easily compute the future and present value of some financial asset. Alright, so now let me introduce logarithmic functions. Okay, so once again, logarithm is defined as the inverse of exponential function. And remember, b to the power x with a positive base b other than 1. When base is larger than 1, monotony increasing, like this one. When base is smaller than, so when base is between 0 and 1, the graph of the function is symmetric with respect to the y-axis, so it's a monotone decreasing, like this one. Okay? And either way, in either case, the function is monotone, either monotone increasing or decreasing. So inverse function exists. Okay, the inverse function of exponential exists, and the inverse is called the base b. So the inverse of b to the power x is called the base b logarithm function. Okay, so if f of x is given by b to the power x, then its inverse is going to be logarithm with base b of x. Okay, so by definition of the inverse function, we know f inverse of x is always equal to x. Right? And we can interchange the order. So f inverse of f of x is also equal to x. That is the definition of the inverse function. Okay? So if we define logarithm as the inverse of exponential function, then we have this one. b to the power log with base b of x. So that is this one. Okay? Composite function between f and f inverse. But the outer function is given by f, the exponential function. Inner function is given by logarithm. Okay? That is going to be x. So if we have 2 to the power x and log with the base 2 of x, then 2 to the power log with the base 2 of x, whenever these two bases are matched, then we have just x. Okay. And if we interchange the outer and inner functions, so now the outer function is given by logarithm, and the inner function is given by exponential function. Then the composite function becomes log with the base b of b to the power x. Okay. Still, we can cancel these two, and we are left with the power x. Okay, so log with the base 2 to the power x, that is x. Log with the base 10 to the power x, that is x. Okay, so whenever the base of the logarithm is the same as the base of exponential function, these two are cancelled, and we are left with just x. Because the inverse of 10 to the power x becomes logarithm with the base 10. Alright, so the basic idea of logarithm is, we know 2 squared is 4. Okay, so 2 to the power x is y. Okay, and if we think about the inverse of this function, then we change, we interchange x and y. So 2 to the y is equal to x. Okay, no, sorry about that. So in the inverse function, we have this one. So log with the base 2 of y is equal to x. Okay, so in this example, y is equal to 4 and x is equal to 2. So y is 4, x is 2. Okay, so in general, log with the base 2 of x, if we want to evaluate log with the base 2 of 4, okay, that means 2 to the watt power is equal to x, or is equal to 4. Okay, that is number 2. Okay, exponential function, the definition of the way to compute exponential function is immediate, right? 2 squared is 4. Okay, and the way to interpret the logarithm with the base 2, okay, no matter what is base. Okay, so if we want to evaluate the log with the base 2 of 4, that means 2 to the watt power gives us number 4. Okay, so for example, another example, log with the base 10 of 100. Okay, so we want to evaluate this, that is 10 to the watt power gives us number 100. That is 2. Okay, so the logarithm with the base 10 of 100 is number 2. Okay, and let me talk a little bit about, so before talking about basic properties, so let me do some examples here. So with the definition of a logarithm, we can solve the some equation involving, I didn't define the natural logarithm or common logarithm. Okay, so I'm done with this part. So, I just explained the logarithm with the base b, but logarithm with the base e and base number 10 have their own notation. So when base is given by number e, so log with base e of x is written as ln x. Okay, so we omit the base e, okay, and then rewrite this log function to ln. And this is called the natural logarithm. Just as we call, e to the power x natural exponential function, and whose inverse function is called natural logarithm. And when base is 10, and we often omit that base, okay, and that is commonly used, so this is called common logarithm. Okay, so log without any base of x, that is a log with base 10 of x, and ln x is a logarithm with base e, number e of x. Okay, so here the graph of a logarithm. So we have a 2 to the power x, that is denoted by function f of x. Then its inverse is going to be log with base 2 of x. Okay, and then the image of the function, the graph of the inverse function, is the reflection about the 45-degree line. Okay, so the graph of 2 to the power x looks like this. Then its inverse function has this image. All right. So now let me solve some equations involving logarithm or exponential function. So natural logarithm of x, that is ln x, once again, ln x is equal to log with base e of x. That is given by 3t plus 5. Here t is a constant. That is a constant. Okay. Then we want to solve this equation for x. Okay. And the way to solve that is, remember, b to the power log with base b of x is equal to x. Okay. So we're going to use this property, the definition of the inverse function. It's the definition of logarithm to solve this equation for x. So now we raise to the power, so we take the exponential function. So e to the power log with base e of x, it should be equal to e to the power 3t plus 5. Okay, because the two exponents are the same, are given to be the same each other. Then the left hand side, e to the power log with base e to the power e of x, then this e and log with base e are cancelled, so we are left with x. So x is e to the power 3t plus 5. Right, so that's the way to solve the equation when the equation involves some logarithm. Okay, so we take the exponential function with the same base, okay, then we can solve for x. So when equation involves exponential function, so e to the power 2x is given by 10. Okay, then we take a logarithm of both sides. So now we are going to use log with base b of b to the power x, that is equal to x. Okay, so using this, we take a logarithm. So log with base e, that is ln. So exponential of 2x is e to the power 2x. Remember, this one is equal to e to the power 2x. Okay, and that is given by 10. Now we take the natural logarithm, so ln of 10. Okay, so I took natural logarithm of both sides. Then the left hand side becomes ln and e are cancelled. So we have just a 2x, that is ln of 10. So x is going to be 1/2 ln 10. Alright. So finally, let me illustrate some basic properties of logarithm. So when base is larger than 0, so once again, the logarithm is defined as the inverse of b to the power x. Okay, and remember we put some restriction on base b. So b is given by some positive number other than 1. Okay, so the base of logarithm should be positive number. Okay, so logarithm is defined only for base, positive number. Okay, so when b is larger than 0, the function always takes the value of 0 at 1. Okay, so log with base b of 1, that is always equal to 0. no matter what base b. Okay, but this is immediate. This is very easy to understand because this is equivalent to saying that b to the power 0 is equal to 1. Okay, so log with base b of x is equal to y, then b to the y is equal to x. Right? So by definition of the inverse function, if log with base b of x is equal to y, then it is equivalent to saying b to the power y is equal to x. Right? So log with base b of 1, that is always equal to 0, because when this exponential function boils down to 1, only when exponent is equal to 0. So logarithm always passes through the point 1, 0. So when x is equal to 1, logarithm takes a value of 0. So it will be through the point 1, 0. Okay? So when and the second, the domain of this function, so the function is defined on the interval between 0 and infinity. Okay? And because this is because b to the power x is always positive. Okay? So now the codomain of the original function becomes the domain of the inverse function. So the domain of the inverse function, domain of the logarithm, should be positive number. Okay? So the graph of this function appears first and the fourth quadrant. Okay? Because when x is smaller than 0, the function is undefined. Okay? So in this region, in the second and third quadrant, the function is undefined. Right? And then the third property is, remember, when base is larger than 1, the exponential function is monotone increasing and looks like this. So when base is larger than 1, this is the graph of b to the power x. So its inverse function is a reflection above the 45-degree line. So it looks like this. Okay? So when base is larger than 1, logarithm is increasing. Okay? And remember, when x grows to infinity, b to the power x also grows to infinity. Okay? So similarly, we have this. If we take the limit as x goes to infinity of log with base b of x, when base b is larger than 1, this is equal to infinity. Okay? But when x grows to negative infinity, we know that is 0. Okay? So interchanging x and y, now when x approaches 0 in logarithm, the image of the function goes to negative infinity. Okay? When base b is between 0 and 1, we have the opposite case. So now the function is decreasing. Okay? But when x is close to 0, the function goes to infinity. When x goes to positive infinity, it goes to negative infinity. Okay? Alright. And then some rules about logarithms. So when we have, for any real numbers x and y, positive real numbers x and y, we have these 4 rules. But these rules are immediate from the exponential function. Remember, b to the power x plus y, that is b to the x times b to the y. So in exponential function, addition becomes multiplication. Okay? So in logarithm, multiplication becomes addition. Okay? So log of xy is equal to log of x plus log of y. Alright? And then in the exponential function, division, b to the x, difference between b to the x minus y is b to the x divided by b to the y. So in exponential function, difference becomes division. So in logarithm, now division becomes difference. Okay, so log of x over y is equal to log of x minus log of y. Okay, and then the power. So whenever we have power in the argument, so x to the power y, and we can bring up this power and put it in front. So that is y times log of x. Log of x to the y is y times log of x. Alright, so this is immediate from the first rule, the product rule, because multiplication becomes addition. So think about log with base b, say 4, okay? And then 4 is, we can decompose into, say, 2 times 2. Once again, multiplication becomes addition, so we have log b of 2 plus another log b of 2, so 2 times log b of 2. Okay, so log b 2 squared is equal to log b, 2 times log b of 2. And then finally, log with base b of x can be written as natural, can be written in terms of natural logarithm. So that is ln x. So ln of the natural logarithm of the argument x divided by natural logarithm of base b. Okay, so we can change the base. We can convert the base b to base e. Okay. So for example, so let me do one example here. So we want to convert this number t that is given by 7 times log of 2y. Okay, so the base is not specified. That means the base is number 10. And we want to convert this quantity into natural logarithmic function. So 7 log with the base 10 of 2y. Okay, so 7 is a constant, so I'm going to leave it alone. And then, in light of this formula, we can change logarithm into natural logarithm, okay, ln x over ln b. So this is going to be ln of 2y divided by ln of 10. Okay, and then you can rewrite this, say, ln of 10 on the bottom, and then because multiplication becomes addition in logarithm, so ln 2 plus ln y. Okay. All right, and then so this is the way to convert general logarithm into natural logarithmic function. And analogously, we can convert general b to the power x, so general exponential function, into natural exponential function. So b to the power x is equal to e to the power x times ln b. So we can write every exponential function with base b, okay, as a power of the natural exponential function. So we can convert any exponential function to natural one. Okay, why this is true? Because think about a b to the power x. Okay, b to the power x. Okay, that is equal to, say, because e to the ln x is equal to x, right? By definition of the natural logarithm. That is the inverse function of natural exponential function. So these two are cancelled. We are left with x. So I can rewrite this b to the power x as e to the power ln of b to the power x. Okay? So, by the property of natural logarithm, this power x comes up front. So I can pull out this power x. So e to the power x ln b. Okay? So this is the way to convert the exponential function to natural one. Okay? We first convert b to e. Alright? And the only thing we have to do is we multiply the exponent x by natural logarithm of b. Okay, so 3 to the power x is equal to e to the power x ln 3, 10 to the power x, e to the power x ln 10, say 7 to the power negative x, that is equal to e to the power negative x ln 7. Okay, that is easy. So we can change every exponential function with arbitrary number of base b to exponential function using this formula. Alright, so let me just do one more example. This exercise, two more examples. So how to convert this function to a natural exponential function? So 3 times 5 to the power 2t. Okay, so 5 to the power 2t, so that's going to be e to the power 2t ln 5. Okay, and then we have constant 3 that is multiplied. So 3 times e to the power 2t ln 5, that is a converted form of this exponential function. Okay, and finally example 10.5, solve the following equation for x. We have a two exponential function combined with a logarithm on the left hand side. So if we first take a look at the first term, 3 to the power logarithm with base 3 of 7, the bases are matched, so they are cancelled, so that is equal to 7. And then 4 to the power log with base 4 of 2, once again bases are matched, so they are cancelled, so that is 2. Okay. So the quantity on the left hand side is just the 5. And on the right hand side, we have 5 to the power this quantity. So 5 to the power x minus log with base 5 x squared. Okay. So once again, difference becomes division in logarithm. So that is logarithm with base 5 x over x squared. Okay, by the quotient rule, difference becomes division. Right? So using this property, using this rule, I can rewrite this quantity as division. So then, 5 and 5 are matched each other. So these two are cancelled. Okay? 5 and log with base 5 are cancelled. So I'm just left with x over x squared, that is 1 over x. Okay? So the right side is 1 over x, left side is 5, so x is going to be 1 over 5. Alright? So let me stop the second video right here, although I'm left with just one more exercise, and let me do this at the live lecture Friday. Okay? So this video is a little bit long. It's longer than 1 hour, but hope you guys enjoy this video and this video is helpful, and I'll see you guys in the next video.